You're listening to Inside the Logic, real talk with FPGA engineers. And this episode is all about high stakes problem solving. You know, timing errors in FPGA systems can feel like an orchestra out of sync. And my guests today, they're going to bring real world stories of one such disaster, what went wrong, and how they fixed it and what it taught them. My name is Kevin Rosenquist. I am your host, and I am here with Charles Sobczak and Ryan Erickson. Charles, Ryan, good to see you guys again.
Good to see you, Kevin.
Hey, good to see you.
So, okay, we're talking about, a disaster, debugging a disaster. So tell me about, you guys have a story you want to tell me. Tell me about the bug or constraint issue that you faced.
Sure. So with our products, a lot of the times customers implement the FPGA card that we use into larger systems, and they use the real digital and analog I/O from the card, the input-output ports, to be able to communicate with either real systems or potentially other FPGA cards or whatever they need fit in their simulation system. And a lot of times, customers will use the firmware algorithms that we have on our FPGA to generate analog signals to communicate with real physical parts. And in the case of this customer where there was an issue, they were communicating with a resolver, which is a type of steering mechanism used in aerospace. And so what was happening was the FPGA design that we had provided for this customer for this solution was we would receive signals from their resolver transmitter, and we would calculate the angle the resolver was at based off of the signals being sent. This is what any resolver receiver would do, but in this case, we were simulating said resolver receiver. And so in the ideal sense, whenever they were turning the resolver in the physical part, you could immediately see the angle changing on the FPGA side. So theoretically, if everything was going smoothly, whenever they changed by 5 degrees on the real part, we would see a change of 5 degrees exactly in the math on the FPGA, reporting back to the computer via the PCIe Express slots inside the motherboard. What had ended up happening was we delivered the system, and they started testing against their real resolver communicating to the FPGA, and we were seeing about a 6 or 7 degree error, which we boast a less than 0.1 degree margin of error for anything that we're doing signals like this. And FPGAs have the benefit of being extremely exact in the math that they do. And so, seeing something upwards of 6 to 7 degrees, that raises the alarms. That sounds the sirens, right? Like something's going on. So we had spent some time trying to figure out what it was. And we were able to kind of break the system up into multiple pieces, because the issue could exist inside of the FPGA code itself. The issue could exist inside the hardware on the FPGA. It could exist inside any hardware in between the FPGA and the real part that they have, or it could be a faulty part that they're using. There's a multifaceted route in which this bug could arise. Since we just know there is a bug, we don't know where it is. So what's really cool is the first thing that we did is we were able to send them and reflash their FPGA, which is the beauty of reprogramming FPGAs, is we were able to reprogram our FPGA to not only be simulating the part that is receiving the signals from their real resolver, but also simulate a real resolver on our FPGA to kind of cut their part completely out of the loop, to see if we could isolate if the issue would still exist without their part even being remotely involved. And so the way we did that was we sent the signals out of the FPGA and back in through the same system back into the FPGA. And then we were seeing the problem still existing. So at that point, it was really cool because we were able to be like, okay, it's on us. It's on our side and for our company. It's not on y'all. It's not, your part's not broken. It's nice to be able to tell the customer exactly, don't worry, you're fine. We'll fix it. It's almost like a customer service thing, right? It's just like, well, let's cancel it. Let's make sure you're fine first, and then we'll take all the blame and figure it out from there. And what was really cool is we have a really nice product in this building called Simulation Workbench, where it is this software that functions on real-time systems that controls multiple I/O cards, in this case, the FPGA card, and any other I/O or control algorithm card inside of these big systems, and it controls them in real time together simultaneously, and you can gather information from the cards, program the cards with information and have this beautiful display that shows all of the information necessary, and as well as like real-time logging and updates. And it was a fantastic tool to use as a customer, but in this moment, it was a fantastic tool to use for debugging, because we were able to see everything that we needed to see, even though we were kind of operating through a customer's computer in the field, because we were on the phone with them we were sharing our screens on Microsoft Teams, and we couldn't have our hands on. So we didn't get an opportunity to actually touch this hardware. We had to figure out the issue from thousands of miles away. And so we were able to use this program that we have to view all of the information on the card, and that's what the customer purchased. They had that program installed. And so in the system, we had the FPGA card sending signals out to two different types of signal conditioning cards, where some form of conditioning on the output signal was being done to shape it and maybe add resistance or load to make sure that we were sending out the exact kind of massaged signal that the real part that they were using wanted, because we want to make sure that we're not going to burn up anything on their end, right? So we knew that the issue that we had in this instance had to either be inside of the FPGA code on the FPGA hardware or somewhere in that signal conditioning. And so what we were able to do is, since we were able to reprogram the FPGA and use Simulation Workbench, to view the data changing in real time, we were able to provide the customer with the instructions of moving the cards out, plugging in things to where you would isolate one card, or just the FPGA in one signal conditioning card, FPGA in both, FPGA in the other one, and just any possible permutation to then identify what exactly was causing the issue. Because if the data is going in and then out, or out and then in, and we're seeing discrepancies in some permutation and not discrepancies in another, then whatever was removed is likely the cause of the problem. And in this case, that is what had happened. There was an issue inside one of the signal conditioning cards. And what was so beautiful about this exchange was it happened so quick. This could have been a problem, and it was a minor manufacturing issue that ended up being, we just moved a jumper on the card from one spot to another that had somehow I believe in this case the jumper had fallen off, and so it was literally like buy a 10-cent part from an electrical shop and just put it right there, and then we're good. It was nice and quick, nice and simple. But what really made this cool is that if it wasn't for the nice meshed relationship between every single one of these parts with Simulation Workbench and our hardware with other pieces of hardware, and as well as how well our hardware meshed with their part, we were able to rule out any just non-ideality uncertainties. Because let's say you buy a blender and you plug it into the wall and it doesn't start. Well, is it the blender's fault? Is it your wall outlet's fault? Is the cord faulty? There's 100 different things it could be. But what's beautiful with our products is we were able to have a level of confidence of, okay, well, we know Sim Workbench communicating with the card, that's not the problem, because it always does it well. We know that the card communicating with the signal conditioning card is not the problem. We know that the signal conditioning card's talking to the real part's not the problem, because so many things have been ironed out and smoothed out. We were able to just isolate the problem so quickly and get everything solved. And the customer ended up being very happy. You can't say who it was, but they ended up being very happy with it. And I believe they're building more systems with that involved. And so it's cool to see, because it's like a full circle story, and it was like a day.
Yeah.
It happened there.
It was a day. That's incredible that it was that fast. Really, actually, very incredible.
Yeah, it ended up being really cool. And I have to give props to the other members and other teams in this building, because we're a company of about 100 people, and our team is only 5. And so being able to just rely and kind of lean on the consistency and execution of other teams is really nice.
It's a great story. It's a great success story too. So what are your takeaways, both of you guys? What are the takeaways from something like this, as far as, it sounds like it was a pretty, seemingly benign problem. Like something happened, something just like fell off or something like that. Fairly simple kind of thing. But what did you learn from, debugging this and all that for the future?
I'd say my main takeaway it was my first instance. I'd only been in the company for about a year and a half at this point. It was my first instance of really seeing the customer service aspect of an engineering small company coming to fruition. if you buy something from one of the massive companies, you got to go through the support line. You got to go make sure you follow their appropriate process, maybe submit a ticket, maybe even just ask a question on their forums. I don't know.
Yeah, you're right. There's so many different ways. Sometimes it's a chat bot, sometimes a ticket, sometimes, yeah, you're right.
And these days, you don't even know if it's a chat bot.
It
could be, And so it was really cool being on the small company side here, is it was interesting to watch the customer relationship be strongly built and fortified, because they could pick up the phone and call the developer engineer right then and there. And there was a question I had in that process, and I walked 2 offices down, asked one of my buddies. I was like, hey, this is happening, I need your insight. And he walked over, and we were both on the phone. And it was my main takeaway is it was really cool to see the kind of mission statement as a small company coming into fruition and coming to life in front of me. It was really interesting.
It sounds like that was actually a pretty good experience for you. You said you were only there for a year and a half at that point. It was good for you to kind of have to do that, so that in the future now you probably you have a little more confidence going into the next problem that could arise.
Oh yeah, 100%. Charles, do you have any major takeaways from that one?
Yeah, I mean, I guess I just think for most engineers, debugging things is kind of a learned skill set, and especially when you come out of school and your focus is kind of narrow. You're focused on you're an electrical engineer, and so you're an FPGA expert. Not an expert, but you at least know all the tools for FPGA. But then when you start with a company, you recognize that debugging is sort of a system level procedure. And so there's a module level testing and a system level testing. And so kind of like as Ryan was suggesting, I mean, he's actually a very talented debugger, but it's definitely a skill set that you have to learn each of the stages. Like he was showing, like your module, but then viewing it from a system level perspective, what is the high probability error where there could be a problem? And then in some cases, it's situations like this where it's something strange that just possibly happened in manufacturing or shipping.
Well, I always love a happy ending, so I'm glad that all worked out for you guys. And thank you very much for joining us on this episode of Inside the Logic, Real Talk with FPGA Engineers. Charles Sobczak and Ryan Erickson, thank you guys both so much. Really enjoyed the conversation.
Thanks, Kevin.
Yeah, thank you for having us.